Um, so in the previous tutorial, we talked about statistical ensembles. So what we're going to do today is to do the exact same thing, but for quantum systems. So we're going to talk about quantum ensembles, or in general, quantum statistics. So, okay, so when we talk about statistics in the context of this course, we have two types of probability. So let's look at some systems. So I have an Hamiltonian, okay, with some eigenstates. Let's call it. So let's say we have only two states to simplify that. So I have either state 1 with eigenenergy epsilon 1 and state 2 with epsilon 2. So in quantum mechanics, we usually say, okay, I can write some wave function that is a superposition of those two states. So I have alpha, for example, multiplied by state 1 and beta multiplied by state 2, and then the probability to measure one of those states, for example 1, will be alpha squared, and then the probability for state 2 will be beta squared. So this is all. Now let's look at something a bit different. So we have a system with n particles and quantum particles, and I'm telling you we have n1 particles in state 1 and n2 particles with state 2. So what's going to be the probability to measure state 1? It's going to be n1 over n1 plus n2. Right? This is just classical probability. And the same for n2. And I can define those to be like, so this will be P1 and this is going to be P2. So we have, in both cases, we have a probability to measure some state, but you agree that those are like very different physical things. So in that case, which is what we talked about usually so far in that course, we have a probability that is a result from the fact that we have many particles in the system. We cannot keep track on each particle. So this is not the measurement is deterministic. So if I have a dice and I'm solving the dice and I'm looking which number I have, so I have a probability to find some number, but basically I can calculate. If I had like some supercomputer, I could calculate my movement, the movement of the hand, and see which outcome I'm going to have. So this is a probability that's come from the statistical nature of the system. But in the case of the quantum superposition, this is a real stochastic process. Like this is something that's resulting from the physical aspect of the system, and the probability is from the quantum nature of this superposition. So if I have quantum particles, so this is going to be quantum gas, I can have either like that type of probability or that type of probability. Now we know how to solve that, and we know how to solve that. Now we want to see what happens when we combine both of them together. So I have statistics of particles that each have like superposition. So how are we going to treat that?
And in the second case, we assume that all these N1 and N2 particles are in pure state, right? It's the strongest assumption.
Yes.
In real life, it's That's
No, you
usually
can
the case.
you can prepare a system with, like, I can prepare a particle in some eigenstate of energy. I have electron that come out from some beam, and I measure the energy of the electron. It doesn't have to be two-state system, but like, you know. And then I know the energy, and then I know what's the distribution of the energy of the electron gas that's out of the system. So far we talked about something called density function, which is the solution of the Wills equation. And now we're going to have a density matrix. So the density matrix is defined as a summation. So I have Pi, and then ket one. And so this is quantum state. So that can be a superposition of whatever states in the of some Hamiltonian. And this is I would call like classical probability. So, for example, in the case that we saw before, if I say, oh, I have 50% of the particles in state 0, in state 1, and 50% in state 2. So this is going to be 0.5 in the probability multiplied by 1 plus 0.5 multiplied by 2. So of course we're not always going to take like a single eigenset. We're going to look what happens when you have superposition, but this is just an example. So this is the density matrix, and in the same way that we had the time evolution of the density function using the Wills equation, now we have von Neumann equation, I think. I think it's like Wills and von Neumann. I don't remember. So the equation is d rho dt So
the partial derivative?
It's not going to matter because we don't have additional coordinates here, but it's defined for derivative. So it's kind of look similar to like Heisenberg picture, but we have a minus because rho follows like the Schrödinger picture and not the Heisenberg picture. So this is like the quantum version of the Wills equation. So this is one thing. What else? So yeah, so we want to do like so the second thing is that rho is Hermitian, so rho dagger equal to rho. Trace of rho is equal to 1. And S time evolution. Yeah. So in the same way that we do in quantum mechanics, if we want to look at like the measurement of some operator, we have an operator, let's call it O. So this is going to be calculated using the trace of rho multiplied by O. So, okay, one last thing before we solve an example. Sometimes people talk about something called pure state versus mixed state. So, the definition of a pure state is any state that the density matrix can be written as using a single wave function. So what does it mean? So if I look at the example that I showed in the beginning, we have a difference if I look at like, I say, okay, I have a system with n particles and I have 50% chance to measure a particle with state in state 1. So I have n1 is equal to, like, let's say 50%. So the density matrix is going to be like, okay, let's ignore normalization for a second. So I'm going to have like a
diagonal matrix.
yeah, but this is okay. This is mixed. We start with mixed. So the probability to measure some state of the system. So let's say I want to measure state mu. Okay. So the probability is going to be the probability. I don't want to do that.
Shouldn't the trace be 1?
Yeah. I say ignore the normalization. Okay, so just take that. So the probability to measure some state mu is going to be the projection of mu on state 1, for example, multiplied by the probability to measure state 1, or the projection of mu on state 2 multiplied by the probability to measure state 2. So this is classical probability from the perspective that I can do this separation. So if I had a pure state, so I have like a wave function that's going to be a superposition of 1 and 2. So I would say I have 50% probability to measure state 1 or state 2. But now if I'm going to look at the probability to measure some generalized state mu, I'm going to have those two terms. So let's call it star and 2 star. Plus some additional term so it will be something like C1 something like that. So I'm going to have additional term that mix in state 1 and state 2. right? Because I have a projection on psi, so I'm going to have something that makes the two.
And here you don't multiply by the probability to be in state 1 and state 2, like.
No, because that's going to be, yeah, this is the star and the 2 stars, so I'm going to have that in addition to, I have something addition that resulting from the yeah,
so
so
you don't multiply by C1 squared and C2 squared.
yeah,
like,
I cannot do this separation. So yeah, I don't want to go too much into that because it's not specifically relevant, but the name can be a bit misleading because in the case of pure states you actually have something that mixes the state, but I didn't choose the name. But the point is that I have, in the case of mixed state, I'm just talking about classical probability, and if I have a pure state, this is just, a pure state is just a regular wave function that we know from like regular quantum mechanics. So I can always write that, I can always define a matrix using this wave function, but I don't have to. So this is just for pure state and mixed state. So let's have an example. Let's look at the spin half system. So we have n particles. And we have 60% in state Z plus and 40% in state X minus. So remember, for quantum mechanics, I can look at the projection in Z direction, in X direction, or in matrices, all of that. So what I want to calculate is the density matrix for t equals 0. So we're going to work in the Z basis because this is just for convenience. So Z plus is going to be 1 and 0, and Z minus, even if we don't have here Z minus, but we still want to write it, is basically 0 and 1. And X minus, if you remember from quantum mechanics, this is 1 over square root of 2, Z plus minus Z minus, which I can write as a vector, 1 over square root of 2, 1 minus 1. So the density matrix is going to be, we define it as summation of pi get from I. So we only have 2 states, so we're going to have summation over 2 states. So we have 0.6 for Z plus, and 0.4 for X minus.
Why did you choose X minus instead of Z
Because
minus?
it's given by, that's you mean the question?
This is mixed.
Yeah, this is mixed state. Because I cannot write that with like a single wave function. Okay, so this so I have 0.6, 1, 0, 1, 0. So this is 0.6, 0, 0, 0. And that's going to be 0.4 over 2 because I have 1 over square root of 2. 1 minus 1, 1 minus 1. So overall I have 0.2 minus 0.2 minus 0.2, 0.2. So O equal to 0.8 minus 0.2 minus 0.2 and 0.
הוקטורים הפוכים, נכון?
Yeah. So.
I think it should have been. Now it's in the product.
Yes, that's fine.
ככה זה.
Okay, so this is all it equals 0. So basically, this is going to be the density matrix for any time that's larger than 0, 2, because we don't have an Hamiltonian here. In the homework, you're going to have an Hamiltonian, and you're going to find the time evolution. But this is like quantum mechanics question, so. Yeah. Okay. Okay, so this is for density matrix. Now let's talk about quantum ensembles.
May I ask you a question?
Hmm?
May I ask you a question? You said that we don't have any Hamiltonian here.
Mm-hmm.
What does it mean physically? I mean that the system has no energy, or
Okay, so no Hamiltonian is not really like a physical system, but
yeah.
you don't have any given like okay, you can have, for example, an external magnetic field or something that interacts with the spin, and then you have Hamiltonian, and then you can find a time evolution. But because you only have the spin of the particles, if you don't have any external force, you're not going to have really time evolution for the system.
But spins are interacting with each other.
Yeah, but those nobody said anything about interaction. Like unless someone said that the spin interact, we don't know if they interact. This is like non-interacting particle.
Okay. It's kind of in artificial system.
Yeah, we are okay. In general, during this tutorial, we're only going to talk about non-interacting particles, because if you add interaction to the system, like this is going to be complicated enough. Now we're going to actually talk about quantum gas. So adding interaction is for like far beyond the scope of the course. So. Okay, so quantum ensemble. So last time we talked about, we have three ensembles that we know from like classical statistical physics. So we are also going to have the exact same ensembles here. The only difference is we're going to write them using the density matrix. So we have the microcanonical, the canonical, and the grand canonical. So, in the microcanonical, we have fixed energy, and fixed volume, and fixed number of particles. So, the partition function is going to be 1 over the number of states with energy E multiplied by the sum of the ket and basically all of the states of the base of all states that have energy E. So this is I in E. So if that was like the regular microcanonical case, that was just like that was just a number.
How the energy can be fixed if you have uncertainty principle?
Wait a second. This is the if we haven't. No, but you have. You look at like. This is like what we did with the harmonic oscillators. So you say, if I have given like. You can know the energy of the system, but then you don't know like something else. So with energy, okay, it's a bit you have uncertainty between energy and time. So this is a bit. It will be a bit weird in that case. I'm not sure exactly how it's going to work, but you can look at like specific given energy, and also you have like you have the energy of all of the system. So you have many particles, and the overall energy of the system is fixed, but the particles themselves can exchange energy, so you don't really know everything about the particles. In the same way that like I can have gas of particles, and I know like the temperature, which is like the momentum of the particles, but I cannot measure the specific momentum. So this is for the microcanonical. For the canonical, we have E minus beta H. Yeah. So we're going to write everything with the operator instead of like a summation. And then if I look at like the summation, so if I look at like the partition function, Z is going to be equal to the trace of E minus beta H, which is basically a summation for matrices. And then same for so the canonical is where I have a heat bath, so the temperature is a constant, and I have fluctuations in the energy. And the non-canonical, I have a particle bath, so I have fluctuations in the number of particles, and I have a fixed chemical potential. So I'm going to have E minus beta h minus mu n, and then z is a trace So basically, anything that we're going to do, so we are going to look specifically in to use the design canonical ensemble in the calculations. Basically, everything that we're going to do, you can also use the canonical and the microcanonical to get the same result because they're all equivalent eventually. But it's just much more complicated. If someone really wants, I can like send you something to see how you do it, because we need to add like additional constraints and stuff, so anything just more complicated. So we're going to use the grand canonical. Okay, so similar to what we defined at the beginning, we have quantum gas. And particles. So now when we talk about n particles, we say we have fluctuations in the number of particles. So n particles is actually the average. So this is n. So it's sum over n. Yeah. So this is the sum over all of the occupation numbers. So I will define that in a second. So for the system, we have an Hamiltonian. So we have the Schrödinger equation, and we have for each energy level we have Ni, which is the occupation number. So that's the number of particles for each energy level. So the average number of particles is given by the sum over all of the occupation numbers, and the average energy is going to be given by the number of particles for the energy level multiplied by the energy level. So this is like a classical average. No, I don't. So, in order to calculate the number of particles or anything in the system, we need to calculate the partition function, like we did with the classical ensembles. So,
But just a second, the Ni is not the probability, it's just a number, right?
Yeah.
And it's supposed to be normalized.
yeah, and Ni is going to be dependent on the probability. Like, okay, Ni is like average number of particles with, so this is like average number of particles with energy epsilon I. So you have number of particles, like average occupation number, and you have overall the summation of all of those occupation numbers.
But aren't you supposed to do like in the entire the total number of particles? By definition, the average, right, is the summation of the probability times the energy.
Yeah, this is going to be this is going to depend on the probability. We'll see in a second.
Okay.
We'll see in a second. Okay.
Right.
This is a bit. That's why I want to add the partition function. So the partition function is basically the trace of the probability, like the e to minus beta h and n. So the trace is basically the summation over all of the possible configurations. So we're going to have the summation over all of the possible configurations of the occupation numbers per energy level. And then in the exponent, I'm going to use the definition of the average energy. So this is beta sum over epsilon I and I. Okay, I hope you can see that. Minus mu sum over Ni. So I have one summation in the exponent of the energy level, and I have another summation of the occupation number. So I can take, this is exactly like we did with the regular grand canonical ensemble. I can take out the summation from the exponent, and then it's going to be a multiplication. So this is going to be multiplication over all of the different values of the energy level, and then I have a summation over Ni, e to minus beta epsilon I and I minus mu and I. So just the transition from here to here, just notice that this summation is not simple summation of Ni, is summation over all the configurations of Ni. So the reason I can do this exchange is that if I do first the summation over the energy and then the summation over Ni, I need to add a constraint of the energy level. So so the reason I'm using the fact that I'm using the grand canonical ensemble is allowing me to do first the summation over Ni. So I don't need to put like by hand the constraint of the number of particles. So okay, so this is a very general formula, and now we're going to have two options. So when we talk about quantum gas, we have two types of particles. So you remember from quantum mechanics, we have either bosons or fermions. So let's start with the fermions because they're easier. So, what happened for fermions? For fermions, you remember Pauli principle. It said that for any energy level, for any state of the system, I can only have maximum of one particle. So I cannot have two particles with the same in the same state. So for each energy level, the occupation number Ni is going to be either 0 or 1. Right? Because I cannot have more than one, so the summation becomes very simple. So Z is going to be, so I have, if Ni is equal to 0, this is going to be just 1, and if it's equal to 1, beta epsilon I minus right?
It's minus. Should be plus.
I have minus here.
No, it should be
No,
plus
no, no.
of the
One
of the
one
E
plus.
minus.
Sorry, yeah.
Yes.
I don't, it's an instinct. Yeah, it's a plus. So this multiplication is over all the energy levels. We're going to leave it for now in that way, and the summation is just have only two terms. So So now, if we want to look at the average occupation number, to calculate the total number of particles as we defined in the beginning. So, okay, we have basically two options. One is to use like you know, you can use either Ni and then like the regular way that we define average. So we have Ni multiplied with the probability. Or you can show from the definition of the partition function that this is equal to, which it's also an equation that we use for like a classical ensemble. So this is 1 over beta, and then we have derivative over epsilon of the ln of z. So you can take the derivative and show that also equivalent. So if we use that to take the derivative of the partition function, so we have minus 1 over beta, and then the derivative of the law going to give me the derivative of z over z, which is going to be that. So this is minus beta e minus beta epsilon minus mu over 1 plus e minus beta epsilon minus mu. And you can see that because I'm going to divide by the normalization, the multiplication is going to cancel out. So I'm only going to stay with like epsilon I, the specific epsilon I that's of the occupation number. So minus beta and minus beta are going to cancel out. I can multiply by the one of the exponents. So this is going to be 1 over e beta epsilon minus mu plus 1.
Epsilon I. Epsilon I.
Yeah. And this is me Dirac distribution. So you probably saw that in like condensed matter or something. So the average number of particles with energy epsilon I is equal to that. Now let's look at bosons. Okay, so we have the same summation, but now it's not going to be that simple because Ni can go from 0 to infinity. If we have bosons, we don't have any constraint on the number of the particles in the same energy level. So this is just so we have infinite summation over Ni, and we can take out the Ni from the exponent, and then it's going to be a geometric sum. So this is equal to 1 over 1 minus e minus beta minus mu. So in the same way that we did here, we can either do calculate the average by the definition or by the derivative of the partition function. And eventually we're going to get, this is E minus. So this is Bose Einstein. So this is Bose-Einstein distribution. Okay, so also the distribution for specific energy level. And the question is why do we even care so much about those distributions? So if you want to calculate something, so if you remember earlier I wrote the average number of particles, overall number of particles, and the overall energy with a summation of Ni. So the problem with the definition is that we are not very good in solving summations, like analytically. So what we're going to do is we're going to use an approximation and write those using integration. So I'm going to look at that.
Okay, then you should integrate over the epsilon instead of the epsilon I in the average E.
What? Yeah, I change between epsilon and epsilon I. Okay, so we had in the beginning we wrote it that. So what we are saying is that we have now another density. So this is actually also something that you saw in quantum mechanics for like a short moment. So the density of state is literally what it sounds like. You have the spectrum of energy levels, and these tell you what's the density of state for each energy levels. So then the density of the energy states. So I'll say in a second how we're going to calculate it. But basically, because the average n that we found here, so this is also true for bosons and fermion. So this is a function of epsilon, and then like if the of epsilon is not too complicated function, you see that this is going to be much easier to calculate than the discrete summation. So how do we calculate the density of states? So you can basically define it for like any general system. We are going to calculate it for for free particle in the box because we are looking at free particles, which is the gas molecules. So if you remember from quantum mechanics, we take particle in the box, and basically what we say is that we take the particle in a size of the box, and then we take the size of the box to infinity. But actually, what's going to happen eventually is that when we find the density of states, it is going to cancel out. So we set the size of the box, but even if the box is infinite, it doesn't matter because it's gives the same results. Okay, so for one particle in a three-dimensional box, so the energy is pi square h bar square 2m s square, and then because we're in three dimensions, we have nx, ny, and nz. Now what we want to find is how many states we have for each energy level. So we have those 3 degrees of freedom, so let's turn them into 1 degree of freedom and call it n. So this is all called n square.
What is the n? What is the n?
N is the quantum number.
Okay.
So we have one quantum number for each degree of freedom. So it's 3 dimensions, we have 3 quantum numbers. So n is like basically kind of a vector, but we look at the absolute value, so it doesn't matter. And then n is going to be equal to square root of 2m square epsilon. So okay, so the overall, so the density is basically the number of particles in the number of states in like infinitesimal range of epsilon. So this is less intuitive to calculate, so we're going to look at the derivative. So we're going to define it as the derivative of the number of states. Okay, I don't want another n, so let's use capital N. Where n of epsilon is number of states with energy, so energy less or equal to epsilon. So we said that n is like a vector. So I cannot plot a 3-dimensional sphere, so let's look at 2-dimension. So we have nx and ny, and we have some radius, which is n. It has a specific value, so this is n. And I want the number of states inside that circle, or in our case, it's inside a sphere. So this is going to be like a 3-dimensional volume with radius n. Okay, yeah, so one thing is that because nx, ny, and nz are all positive, so we're only going to take, if you look at like the 2-dimensional case, we're only going to take like that part of the volume. So if you look at 3 dimension, it's going to be 1/8. So this is overall 4 over 3 pi square and 3.
Pi square.
No, it's 12. Well, n is equal to that. So n to the power 3 is square root of 2n l square, and then epsilon 3 over 2. Then the density state, which is what you're looking for, is the derivative of that by epsilon. So it's going to be, you don't care about the coefficient, so this is going to be, go like epsilon to the power of 1 over 2.
Why don't we need the coefficients?
You can calculate the coefficient, but I just want to show how to get the density. Okay, so the last part. So let's talk what happened from like a physical point of view. So first of all, for bosons, this function, we can calculate everything explicitly, and we can solve this integral numerically. And this is going to give us a function, some general function that depends on the chemical potential, on U, and on the temperature.
It will be zeta function.
What?
It will be zeta function.
I don't know. It's just going to be a function.
I mean, I solve such integrals. Usually it's zeta of something.
Maybe,
and gamma.
but maybe. So the only thing that we care about is that the solution of this integral only exists for, so if you look at like, if you plot this function, so this is all overall equal to the average number of particles. So we can look at mu. This is mu over t, just for technical reasons, because this is how we usually give a product. So for any given number of particles, we can look at the chemical potential as function of temperature, and we see that we have some critical temperature. So above some temperature, we get some function. We don't really care too much about that. But below some temperature, this function, this is going to be unsolvable. So this is going to be the integral not going to be solvable. So what we're going to actually have is that you don't have conservation of the average number of particles. So if we ever talked about Bose-Einstein condensation, we have you have like a gas of bosons, and then if you go below some temperature, what's happened is that all of the particles going to like collapse into the ground state energy of the system. So if you look at like the integral, it's going to look like some of the particles disappear because they're all going to occupy the same energy level. So this is what's happening for bosons, and then the other part is that you see that the chemical potential that we get is negative. So where we think about chemical potential, let's say we have a box, and this part of the box have mu1, and this have mu2. So if mu1 is larger than mu2, the particles they want to go to the place that have the lower chemical potential. So they're going to go from here to here. So negative chemical potential is like an attractive force. So if we have a negative chemical potential for bosons, it means that the bosons act like attractive force. So this makes sense when we look at like the lower energy levels, because they kind of like they all collapse into the same states. But if we're going to look at the fermions, so let's look at the limit of low temperature, like we did here. So T go to 0. So the average occupation number. So this is the Fermi-Dirac distribution we got. So So if you take the limit of the temperature go to 0, it means that beta go to infinity. So if the temperature go to 0, so all of the fermions going to go into the lowest available energy level, but they cannot go all to the same energy level like the bosons. So they're going to occupy like, so this is like epsilon 1 and epsilon 2 and epsilon 3. So they're just going to occupy like one at a time. So we expect the average number of particles for each energy level to be 1. So for the lower energy level, of course. So in order for that to happen, we need E to beta epsilon minus mu to go to 0. So if beta go to infinity, we need mu to be positive, or specifically to be larger than epsilon. So mu have to be larger than epsilon, or at least the lowest value of epsilon, so the lowest energy level. So mu is larger than 0, and it means that we have like always have for that case a positive chemical potential. So they're going to behave like repulsive. It's going to behave like repulsive force, which makes sense because we know the fermions kind of repulse each other from point of view of like they cannot occupy the same energy level. So this is like the way it's looked from like the potential point of view. So this is like the main difference between those two. What else? Yeah, okay, I think that's it. Yeah, okay. Questions?